Assalamu alaikum everyone. My name is Ibrahim Abdul. I am one of Group 7 members in the ODE subject. In this part, I will introduce our project in ODE. Firstly, I want to define the ODE. The ODE is the ordinary differentiation equation, and it's very important in engineering and applying science because they help describe how things change over time, such as the electric circuit, mechanical movement, and heat flow. This project looks at how to solve both first order and second order ODE, as well as the system of ODE. It includes both exact and computer-based methods. The goal is to strengthen understanding of the theory and improve practical problem-solving skills. This project consists of the three parts. The first part is the first order ODE, and to solve it by separation of variable and linear ODE and other methods. The second part is the second order non-homogeneous ODE. It solved it by methods of undetermined coefficient and derivation of matter and parameter. The third part is the system of first order ODE, solving by using the matrix method and the eigenvalue are non-homogeneous terms by undetermined coefficients. My other member is Muhammad Al-Muhtasim Al-Muttaba Isa.
Assalamu alaikum. My name is Mustafa Muhammad Isa, and I will be explaining question one. Number A, we are giving the first order ODE as sine 2x times dy over dx equal y times cosine 2x. We're going to find the practical solution y for the differential equation using the separable variable method, and the initial condition is given as y pi over 4 equal to. First, we're going to separate the dy with the y and the dx with the x. And as you can see, in these three steps, we separated the dy with the y and cosine with the dx. So we have dy over y equal cosine 2x over sine 2x times dx. And then we integrate both sides. We integrate the left side and the right side. The right side integrate using substitution by u, as u equals sine 2x and d equal 2 cosine 2x times dx. So we have half du equal cosine 2x times dx. And after that, we have the left side as ln y. And we're gonna get rid of the ln using the exponential. And after we solve 2y, we are left with y equal the square root of sine 2x times a. And after that, we apply the initial condition y pi over 4 equal 2. And after applying that, we have sine 2 times pi over 4, which is going to be sine 90. It's going to be equal 1. And then we will have the square root of 1 times a equal 2. And then when solving to a equal 2 over the square root of 1, which is 1, and then a equal 2. So we're left with y equal 2 times the square root of sine 2x.
Now with MATLAB code for question number 1, starting with sims yx. This command have two things to do: declares x as a symbolic variable, it do it automatically, and also declares y as a symbolic function of x, meaning that we can use y as a function of x. After that, we will define a variable with the name ODA, and we will put our equation, and you can see that sine 2x times diff yx. Diff yx is the equivalent of dy over dx. After that, we will define a variable with the name condition a, and we will put our initial condition inside it, and then we will define another variable with the name of solve a, and we will use the function dissolve, which can dissolve which can solve ordinary differentiation equation, and we will put two parameters, the equation we have and also the initial condition. After that, we will display our solution using the simplify function, which can simplify the overcomplicated terms in our last solution.
For question 1b, we have x dy over dx plus 4y equals 6x squared minus 5x with initial condition y1 equal 1. First, I will convert this to standard linear form by dividing by x. Dy over dx plus 4 over x times y equal 6x minus 5. This is now in the form dy over dx plus bx y equals qx, where bx equals 4 over x and qx equals 6x minus 5. Next, we integrate factor I equals e to the integral bx dx, which is e to the integral of 4 over x dx. This gives us e to the 4 ln x, which equal x to the 4th power. Multiplying the entire equation by the integrating factor, y times x to the 4th equals the integral of 6x minus 5 times x to the 4th power dx. Expanding y times x to the 4th power equals expanding y times x to the 4th power equals the integral of 6x to the 5th minus 5x to the 4th dx. Integrating y times x to the 4th equal x to the 6 minus x to the 5th plus c. Dividing by x to the 4th, y equals x squared minus x plus c over x to the 4th. Applying the initial condition, y1 equal 1, 1 equals 1 minus 1 plus c, so c equals 1. Therefore, our practical solution is y equal x squared minus x plus 1 over x to the 4th power.
Now moving to MATLAB code for question Q1b, starting also with sims yx. After that, we'll define a variable with our equation inside it. After that, we will put our initial condition, and we will use the solve function again, and we will display our last solution using simplify function also.
First, for question 1c, we have 2y minus x times dy over dx equal y with initial condition y2 equals 3. First, we need to rearrange this into standard exact form, which is 2y minus x times dy minus y dx equals 0. This gives us m equal negative y and n equal 2y minus x. To verify it's exact, we need to check if partial m over partial y equals partial n over partial x. Partial m over partial y equal -1 and partial n over partial x equal -1. Since they're equal, this is indeed an exact differential equation. Now we need to find solution function y(xy), starting with the integral of m with respect to x. I equals the integral of -y dx plus fy, which give us I equal -xy plus fy. Taking the partial derivative with respect to y, partial I over partial y equals -x plus f prime of y, and this must equal n. So -x plus f prime of y equals 2y minus x, which means f prime of y equals 2y. Integrating fy equals y squared plus c. Therefore, ixy equals negative xy plus y squared plus c. The general solution is negative xy plus y squared equals c. Applying the initial condition, y2 equals 3. We have negative 2 times 3 plus 3 squared equals c. So c equals 3.
Moving to question number 1c, exact to the starting with simes yx. After that, we define a variable to put our equation in it, and also define another variable to put our initial condition, and start solving the equation using the solve function. But this time we will put implement to true. And what exactly implement do? It tell the MATLAB code to not isolate y from the equation, so that we can see like yx equal to c, for example, in the MATLAB code, because MATLAB automatically try to separate y from x's. After that, we display our general solution, and to solve the value of c, we define a variable with the name of c and use a function subs, which is the substitute any value, replace or substitute the value of x and y to any value we want. So we will set x to 2 and y to 3. After that, we will display our specific solution to y.
Question 2a. We have second order non-homogeneous equation y double prime plus 2y prime plus y equal x squared minus 1. First, we need to solve the initial equation y double prime plus 2y prime plus y equals 0. The equation is m squared plus 2m plus 1 equals 0, which factors as m plus 1 squared equals 0. This gives us a repeated root m equals negative 1. So the solution is yc equal a times e to the negative x plus b times c times e to the negative x. For the partial solution, since the right side is x squared minus 1, we need to assume yb equals cx squared plus dx plus e. Taking derivatives, yb prime equal to cx plus d and yb double prime equal to c. We then substitute into the original equation 2c plus 2 times 2cx plus d plus cx squared plus dx plus e equal x squared minus 1. Expanding and collecting the terms, we end up with cx squared plus 4c plus d times x plus 2c plus 2d plus e equal x squared minus 1. And then we compare coefficient c equals 1, 4c plus d equals 0, 2c plus 2d plus e equal negative 1. Solving c equals 1, d equals negative 4, and e equals 5. Therefore, yp equals x squared minus 4x plus 5. The neural solution is y equals a times e to the negative x plus b times x times e to the negative x plus x squared minus 4x plus 5.
Now with the MATLAB code for question number 2, non-homogeneous ODE. It's quite simple and short, starting with simes yx. After that, we put our equation in a variable. After that, we use the solve to solve it, and after that, we display it in a message using simplify function.
For question 2b, now we will solve the same equation using variation of parameters. We already found the solution, the complementary solution, with y1 equals e to the negative x and y2 equals x times e to the negative x. And then the one scan is the determinant of the matrix with y1, y2 in the first row and y1 prime, y2 prime in the second row. This gives us w equals e to the negative 2x. For variation of parameters, I need to find u and v, where u equals negative integral of y2 times fx over y over w dx, and v equal integral of y1 times fx over w dx. Here fx equals x squared minus 1. For u equals negative integral of x times e to the negative x times x squared minus 1 over e to the negative 2x dx, which simplifies to negative integral of x cubed minus x times e to the x dx. Using the tabular method for integration by parts, we get u equals negative x cubed minus 3x squared plus 5x minus 5 times e to the x plus a. For v equals integral of x squared minus 1 times e to the x dx. Again, using the tabular method, I get v equals x squared minus 2x plus 1 times e to the x plus b. The practical solution is yp equals u times y1 plus v times y2, which after simplification gives us the same result, x squared minus 4x plus 5. So the general solution matches what we found with undetermined coefficients.
Now MATLAB code for question number 3. In this part, we are solving a system of two first homogeneous differentiation equations. We first define y1x and y2x as a symbolic function, signs. Then we set up the system. The first equation says dy1 over dx equal y2, and the second side says dy2 over dx equal minus 4 times y1. This is classic second order. We solve both equations at once using the dissolve function, which returns the symbolic solutions y1 and y2. Finally, we use simplifying function to display our last solution.
For question 3a, homogeneous system of first order ODEs, we have y1 prime equals y2 and y2 prime equals negative 4 times y1. First, we need to write this system in matrix form. We have y prime equals a times y, where y is a vector containing y1 and y2, and a is our coefficient matrix. The matrix A is a 2 by 2 matrix whose element first row is 0 and 1, and second row is negative 4 and 0. Next, we need to find the eigenvalues. We will solve the equation by determinant of A minus lambda times I equals 0. This gives us the determinant of the matrix with negative lambda and 1 in the first row, and negative 4 and negative lambda in the second row. Expanding negative lambda times negative lambda minus 1 times negative 4 equals 0, which gives us lambda squared plus 4 equals 0. Therefore, lambda squared equals negative 4. So our eigenvalues are lambda 1 equals 2i and lambda 2 equals negative 2i. Now we need to find the corresponding eigenvectors. For lambda 1 equals 2i, we need to solve a minus 2i times I times v1 equals 0. This gives us the matrix with negative 2i and 1 in the first row, and negative 4 and negative 2i in the second row. We then multiply by v1 equals 0. From the first equation, negative 2i times v1 plus for negative 2i times v11 plus v12 equals 0. So v12 equals equals 2i times v11. Choosing v11 equals 1, we get v1 equals the vector 1, 2i. For lambda 2 equals negative 2i, following the similar steps, we get v2 equals the vector 1 and negative 2i. For the general solution, since we have complex eigenvalues, we will need to use Euler formula, and the real part of v1 times e to the lambda 1 x to the lambda 1x give us the vector cosine 2x negative 2 sine 2x, and the imaginary parts give us sine 2x 2 cosine 2x. Therefore, the general solution is y1 equals c1. Therefore, the general solution is y1 equals a cosine 2x plus b sine 2x, and y2 equals negative 2a sine 2x plus 2b cosine 2x. For question 3c, we have non-homogeneous system y1 prime equals negative 3 times y1 plus y2 plus x, and y2 prime equals 2 times y1 minus 4 times y2 plus e to the negative x. We're given that the eigenvalues are lambda 1 equals negative 2 and lambda 2 equals negative 5, with corresponding eigenvectors v1 equals 1, 1, and v2 equals 1 and negative 2. First, we need to write the general solution for the homogeneous system y1c equals a times e to the negative 2x plus b times e to the negative 5x, and y2c equals a times e to the negative 2x minus 2 minus 2b times e to the negative 5x. Now we need to find the practical solution using undetermined coefficients for the term x in the first equation. We will assume yb1 equals ax plus b for y1, and yb2 equals cx plus d for y2, and taking derivatives, yb1 prime equals a and yb2 prime equals c. We substitute into the first equation a equals negative 3 times ax plus b plus cx plus d plus x. Expanding, we have a equal negative 3 ax minus 3 b plus cx plus d plus x. Comparing coefficients for x terms, 0 equals negative 3a plus c plus 1, and for the constant terms a equals negative 3b plus d. And then we substitute into the second equations, c equals 2 times ax plus b minus 4 times cx plus d. Expanding, c equals 2ax plus 2b minus 4cx minus 4d. Comparing coefficients for x terms, 0 equals 2a minus 4c, and for constant terms, c equals 2b minus 4d. From 2a minus 4c equals 0, we get a equals 2c, and 0 substitute into negative 3a plus c plus 1 equals 0. We have negative 6c plus c plus 1 equals 0, so negative 5c equals negative 1, giving c equals 1 over 5 and a equals 2 over 5. We now work through the constant terms equations. We get b equals negative 9 over 50 and d equals negative 7 over 50. For the e to the negative x term in the second equation, we assume yb equals a times e to the negative x for y1 and b times e to the negative x for y2. And then taking derivatives and substituting, we get the system negative a equals negative 3a plus b, which gives b equals 2a, and negative b equals 2a minus 4b plus 1. And then substitute into b equals 2a, we have negative 2a equals 2a minus 8a plus 1, which gives 4a equals 1. So a equals 1 over 4 and b equals 1 over 2. The complete practical solution is y1b equals 2 over 5x minus 9 over 50 plus 1 over 4e to the negative x, and y2b equals 1 over 5x minus 7 over 50 plus 1 over 2e to the negative x. The general solution is a sum of complementary and practical solution. And finally, applying the initial conditions y10 equals 0 and y20 equals 0, we solve the system to get a equals negative 1 over 6 and b equals 29 over 300.
Now with MATLAB code for question 3C. Non-homogeneous system with initial condition. Starting with sims y1, y2, x. After that we put every one of our two equations in a different variable and also their initial condition. After that we will use define the solve function to solve it at the same time, and in the last we will display each one of them using simplify function. As we can see in all our codes, it's exactly the same as our manual calculation.
Finally, in this project, we were able to solve coordinate differential equation using both manual solution and the software method. For first order OD, we use technical like separation of variable and integration factor. For second order equation, we use methods such as determine coefficients and derivation of parameter. We also solve the system of ODE using eigenvalue analysis, and we checked our answer using MATLAB, which helped it confirm that our manual solutions were correct. This showed how the theory and computer tools can work well together. Overall, the project improved our problem-solving skill and deepened our understanding of how ODEs are used in engineering. This method will help us handle more advanced problems in the future. Thank you so much and goodbye.